Okay, kids, we're back here doing more physics. Section 3.1, practice question 9. 9A, it says calculate Earth's force of gravity on each of two steel balls of masses 6.0 kilogram and 12.0 kilogram. So let's first draw in our little G here. Let's draw these two. So here, mass of this one, we'll call it mass 1, is 6 kilograms. And mass 2 is 12 kilograms. You notice I don't care about negative or positive. They're scalars. It's not a directional based quantity. All right. Now let's draw, like if we'll make an exception. We'll let this free body diagram be circular. It's not the end of the world. Force of gravity 1 on it. And the other name for force of gravity is weight. Okay. And let's draw it over here. Force of gravity on the second object. Weight, second object. They're the same thing. All right. Now, what do we want to find? We want to find the force of gravity on these. So we want to calculate force of gravity. That's what we want to do. Now, we use the standard equation. Force of gravity is equal to the mass of the object. Okay, so listen to what I'm saying. The force of gravity is equal to the mass of the object multiplied by the gravitational field strength near the surface of the Earth. So this is all about near the surface of the Earth. When you see F little g and little g, this is all about being near the surface of the Earth. Nowhere else. Okay, so there's my analysis. And now I'm going to substitute. So force of gravity on the first object is 6 kilograms times negative 9.8 newtons per kilogram. Force of gravity on the second object is 12 kilograms times the gravitational field strength near the surface of the Earth. And now we're going to solve for this. Force of gravity 1, first object, is negative, because it's a vector, 58.8 newtons. Where do I get newtons from? Look, doink, doink, cancels, right? Force of gravity on the second object. Negative 117, that's a 7, 117.6 newtons. Okay, now those are the numbers you got. Terrific. So now that's A. But B is asking, well, hold on a second here. One's got a bigger force on it than the other, right? But in the previous work we did, we learned that all objects fell with the same acceleration of negative 9.8 meters per second squared. How is that possible if one's got a bigger force on the other? Mr. Zafiro, you're lying to us. Actually not. I'll show you. So this is part B. Okay? So here's the first object. Object number 1. Here's a true free body diagram. That is the only force acting on the object, because we are going to ignore any type of air resistance. Okay? So, because part B says, if the force of gravity on the 12 kilogram ball is greater than that on the other ball, why do the two balls accelerate with the same rate? Well, we're going to find that out. Watch. Remember our friend F net. So let's say F net on the first object. Okay? And you're going to be using this equation a lot in this chapter 3. Okay? F net first object is equal to mass of the first object, right, times acceleration of the first object. But you have to also remember that F net on the first object is equal to the sum of all the forces acting on that object. Whenever you write, listen to me carefully, whenever you write this version of F net, you must always write the other version of F net. One is from Newton's second law. The other one is saying, look, we have to add up all the forces. They always work together. This is a huge part of this chapter 3, these two equations together. Okay? So, watch. I'm going to take this and plug it into there because it's the only force on it. And I get F, force of gravity on the first object, is equal to the mass of the first object times the acceleration. Okay? Now, I'm going to rearrange this. Acceleration of the first object is equal to force of gravity on that first object near the surface of the Earth divided by its mass. Which equals, now the force of gravity on the first object, what was it, 58.8, I think? Negative 58.8 newtons divided by the 6 kilograms. Oh my goodness, it's negative 9.8 newtons per kilogram. That's what it is. It's negative 9.8 newtons per kilogram. But what you have to realize is if you take a look at newtons per kilogram, a newton, if you take a look at Newton's second law, F net equals ma. Take a look at this. A newton is equal to a kilogram times a meter per second squared. You get the kilogram from the mass, meters per second squared from the acceleration. So really a newton is a kilogram times a meter per second squared. But I still have a kilogram on the bottom, so they cancel out. Look what I have left. Meters per second squared, which is proving to you that a newton per kilogram is mathematically equivalent to meters per second squared. They're mathematically equivalent. Some of you are daydreaming, I can tell. You need to be focused for an extended period of time. They are mathematically equivalent. I just proved it to you right in here. So, okay, we did it for the first one. We proved that no matter what the force of gravity was on it, when you divided it by the mass, you get the acceleration due to gravity. Will it work for the second one? Let's find out. Let's use the work we already learned. Let's use the work we already learned, okay? And say, look, acceleration second object is the force of gravity on the second object divided by the mass of the second object. We're going to not redo that work we did. We're just going to take advantage of it. So this was negative 117.6 newtons divided by 12 kilograms. Negative 9.8 newtons per kilogram, which is the same as negative 9.8 meters per second squared. So both of them have the acceleration. Now that is the mathematical explanation of this. That's the mathematical explanation of this. And this is what I was hoping you would look up if you didn't get, or ask me if you didn't get. And now I'm hoping this shows you how this mathematically works out. But there's another argument to be had here. Watch. This is 6 kilograms. This is 12 kilograms. They both fall at negative 9.8 meters per second, even though the force of gravity on this, force of gravity 2, is bigger than force of gravity 1. The reason, if you want a qualitative explanation, the reason they fall at the same negative 9.8 meters per second squared is, yes, this force here is bigger. I get it. But this mass is bigger. And the more mass an object has, the more inertia it has, and the harder it is to accelerate it. So it's a trade-off. Yeah, you got a bigger force acting on you, but there's more there to accelerate. So it always equals out to negative 9.8 meters per second squared when you're talking about objects of different masses falling towards the surface of the Earth due to the gravitational field strength near the surface of the Earth, and we are ignoring air resistance. Did you see how detailed I was in my last sentence there? I didn't leave anything to guessing. That's the level of detail we have to approach, okay? That's the level of detail if you're going to be an engineer and you're going to design a road or a bridge or a sewer system or work in a plant that makes who knows what chemicals. Maybe you want to be a chemical engineer or design a circuit if you want to be an electrical engineer. High attention to detail, being focused for an extended period of time. Okay, thank you.